but we'll give it a try anyway. What happened here? I think something flashed on the screen there, but it's gone now, and my computer just kicked into high speed, so it's probably running away. So now let's try to finish the program. Okay, so let's start with in20. There we go, end program. So we can either have it just loop here on itself, or we can have it jump up to the beginning and restart the whole program. Basically, we can make it be the same as clear, fundamentally. Jumps to dice, which is the beginning of the program, which clears the screen. So, you know what, let's do that. This guy relies on the fact that total was set to 0, which is fine, but we could add an instruction and make it do it right. I am trying to minimize my changes to this code up here, though. But all of these guys have to be changed to jumps to somewhere. Let's see how much the image changes if we just put in a jump to dice. So now this guy's going to jump right back up here and start again. Now I didn't clear the count, but that's fine. We'll look at that later. So now if I make dice.hex, which wasn't what I need, I should be able to just do make, actually. Being that I have to manually dump it anyway. We can actually change that, though. Let's make it so every time we build the program, it just dumps out what the program looks like. The program's so tiny, will probably be helpful. There we go. And so now if I make clean, make clean all, make. There we go. So it built, and we got out our program. Actually, okay, so the program's the same size. We can do kdiff3 of the program of the hex file, which we didn't build. So you have the 7 C's to the 0 1s, and then you have right here at CD20, which CD is now an EBA4, which is probably a jump back. It's got to be an immediate value by A4. That's, you know, a thing. So trying to keep this change minimal is probably going to cause me trouble in the long run, but we're still going to work at it. Okay. So now we're going to try to replace one of these move 9 into AH in 21s with a call. And I think that that's still going to be the same size because we're going to go from 2 probably 16-bit instructions to 1 32-bit instruction, because it has to store the address to jump to. So let's try this. So this is going to be call writeLine. Yeah, writeLine. writeLine. Oh, it's right here. Do we have any more in 21s? Wow, we don't even have any more ints down here. So let's see how much that changes everything. Let's make dice.hex. So I built the hex file. Looking for this Pt4 for the $sign. So move back. Right, well, I'll bring up kdiff and you'll see. It's going to say everything's different now. So it starts the same. So here was the CD21. But before that was the write9. This was probably writing the 9 into the A register. This is the interrupt. And also this B101. Right, because after this was, oh no, B400. Yeah, so this guy shifted back a byte. So it looks like it's 1 byte less now to call it. So we're losing our, but that does give us a chance to, we could make it up by writing a value. It's probably not worth trying to maintain, to be totally honest. So on that note, we're actually going to just let it go. And because of that, I want to put in an, if everything else is going to go, I'm going to put in another move. Got to change something. I'm doing a lot of tabbing when I write assembly. There we go. Because I'm trying to align these columns. Okay, so we're going to move into the word. We don't need to reseed when we exit or clear, but we do want to reinit, write 0 to it. So actually we can just cut and paste that line, right? So here's where we write 0 to the total. Let's just move that up here. Now that that's up there, if anything causes us to restart, so either of these, I'm going to go back to dice and that'll reset our total. And we don't really care if the die resets, so we're going to let that slide. So the next thing we're going to do is we're going to modify the string printing. So now we come in, it writes word, we clear the screen, which maybe we'll replace that too, but then it's going to write the menu. Then when we hit T, it's going to write the dashed lines. So if we create writeLine, we'll be able to test the input and if we can write a line. So the first thing we're going to do is we're going to change the termination of this. Because terminating on a $sign, very DOS, but not very modern. So we're going to terminate it on a 0. This way we can have $signs in the strings we write. We can't have zeros then, but that's okay. 0 is an ASCII character pretty much designed for this purpose. So we're going to follow the same pattern that it used, which was we're going to assume that dx is pointing to, well, let's look that up again. So if we look at in 21, 9, right, it takes the ds-dx segment, data segment dx, and writes that string. Now what we're going to do, so we need to choose an interrupt that can output some text to the screen. Unfortunately, there is a print a character in here. Oh, wait. 13 has its own write string, but I think this one needs to know the size. And if we need to know the size, that means we got to iterate through the, oh, here it is, write character in TTY mode. But let's look at this 13, because maybe they do something that we're, this is a mostly great, like it's got lots of detail. Unfortunately, I don't know how, say if we hack the link. There we go. Here we go. I highly recommend this tripod.com site. Let's see. So we wanted to look at, I think I looked at this the other day. You can see it has a lot of stuff here. Subservice, which I have to figure out what that even means. Display page, but here's a big one, is you need to know the length of the string. And then it takes a pointer to the string to write, and that's not as helpful as we'd like it to be. This looks like a very useful function, but then you have to know the length of your strings, which I guess in this case we do. We could change our strings to size followed by the string rather than null terminated strings, but null terminated strings just give you so much more flexibility. And if I decide to, I might reuse this routine later, and it's closer to how the other one works. There's a reason that, DOS made a write, even though, because they had this one available to them as well, but they were like, no, let's make one that's terminated instead. Because so often you're reading in a string and you don't know how big it is until it's, and so then you have to put a terminator on it, and then you read the terminator. It just ends up being a mess. As if we just want to write a character in TTY mode, you have to set a foreground color, but only in graphics mode. You have to set a display page number. What is the display page number? I don't want to write to the active page. What's weird is being that these don't overlap, they could have used the same half register, though I guess this would have given you the opportunity to change it so that you could set the page number and foreground color. But the big thing is we need to set our AL to the character we want to write. Unfortunately, it doesn't describe what a display page number is. Wonder if... Let's look it up. This is just the Wikipedia page that we already saw, and it probably doesn't describe what this display page number is. We could set it to 0, which is statistically... Actually, let's see. AH 0E, right? This is page number. You probably just set it to 0 or leave what it is. Yeah, so you draw character. So you just set it to 0. We're going to set it to 0 and see if that gets us what we need. I think it's most likely to work with 0. And so we're going to just set the whole BX register to 0. So when we write a line, we're first going to move into... First, we don't want to destroy all the registers, right? Like, in particular, this guy's using AL. We're going to destroy DX. So let's look at what that int21 one used. And obviously, AH gets stepped on. Returns nothing. DS, DX. The user can't be assuming that these are going to be fine. So we're going to change DX, because we'll probably use that as an iterator. Let's push some values onto the stack. So when you're writing a function, it's the responsibility of the... Well, you can split up the responsibility, but you want to push any register that you might be using that somebody else might, that isn't part of your interface, so that if it gets crushed, somebody wasn't planning on using that. So we're going to push CX. Now there is x86 ABI that standardizes what C functions do. We're not going to do that though. We're just going to push and then restore any register we think we're going to want to use. We're going to push CX. So actually we have to look at this interrupt, right? This intend interrupt, because it's going to modify AX and BX. So we're going to push, and I like to push them and pop them in alphabetical. We'll push them in alphabetical order, pop them in reverse alphabetical order. Actually, there's a x86 instruction that pushes multiple registers at once. Let's check that real quick. Okay, so there's a push all, slow, as one would expect, because it's going to push all the registers. But it does conserve space, and space is our primary premium here. So on that note, we are going to we're going to push them all. This function, we do care a lot about speed. Anyway, so we're going to push all the registers. And then we're going to move into BX, X0. We'll put a hex on there even though it's... So that makes that 0. And then we were going to put into AH0E, and then we can use AL. That is a good point. How do I say the AH register? I have it not think I'm saying a hex value. AL works. I mean, this is probably just a syntax highlighting problem, not a... The assembler is probably smart enough to figure out what I'm trying to do here. It's weird though. Okay, another point against Kate today. So now what we want to do is we want to move what's pointed to by DSDX. Our default operations are done in the data segment, so we don't even have to specify that. But we can move into AL the byte pointed to by DX. Now this comes down to, I'm not 100% certain what the and ideally I'd like to post increment DX if I can. Should be addressing modes. Label, relative, base index. Yeah, there's not a post increment mode in 86 because you have actual pop and push instructions. Register indirect. That's what we want. Default segment register, data segment. I'm assuming that this is going to be the same for DX if it's for BX, because it's probably just if you're using the base pointer that it uses the, I forget which segment that is. System segment? Something like that. I mean, theoretically, we shouldn't even have to say that this is a byte. I mean, it should know from the fact that we're putting it into AL. Save registers. Set up for int function selection. We could even say int 10. Get character. Then now that we have the character, what we next want to do is we want to check to see if it's 0. The question is, is the move going to test it against 0? Some architectures it does. Does it in x86? Move byte or word. Flags not altered. It's not altering the flag, so that means we have to manually test it against 0. So now that we've gotten it, so let's test it. So test, compare, AL and 0. So, and then we're going to jump not 0. That means they're not equal to display char. Now, if I was smarter, as I said, I could. There were those local symbols, but we're going to make it a not local symbol. And so if we get here, though, that means that it was 0, which means we're at the end of our string. So we don't need to print anything else. What we need to do, though, is restore our registers. We're going to pop all the registers. And then we're going to return. Oh, now we're going to comment return. So otherwise, we're going to get down here to display char. So in order to display the character, we have to call the interrupt. So int 10, and then once we display the character, so yeah, this we're going to have to increase dx. If I remember correctly, there's an increment instruction, but we have an instruction reference, so we might as well use it. Inc, yep, inc does update the flags. Then we're going to increment dx, and then we're going to, then we can grab the next character. Jump next char. Actually, we'll call it get char, which is right here. So we get a character. If it's not 0, we display it, and then we get the next character and display it, and get the next character and display it. Eventually, we'll hit a 0, and then instead we'll pop all the registers and return. So that is our entire writeLine function. Pretty simple, right? So let's try to make it. We got an error. What's our problem? Reserved word uses symbol. Right, like this is literally what I'm trying to do. I mean, admittedly with a byte register. Oh, is that line? I'm doing it wrong. AX is a register. You can move into it. EX, register indirect. Let's try a different register. Let's grab one of the more direct examples I have here. So they're moving from BX to AX. This is extended, but that's just, I mean, unless you need to be 32-bit support to do that, but let's just try it. If I go BX, does it work? It works from BX, not from DX. Is this one of those things that I just can't do it with DX? And okay, this makes a lot more sense. So I'm just assuming, like, okay, well, there we go. That comes back here, and I guess I should have figured that out from this. When I'm in here in the addressing modes, this one means literally I can use these 4 registers. So I have to use one of them, and BX is already being used. So, and base pointer is not relative to, so I'm guessing we're going to use the data index register. So instead of using dx here and here, we're going to have to first, no, we'll just change where we use dx up here. So we're going to use di. Let's make sure that builds first. Cool. Okay, so now that that built, that means we can't use dx over here. So let's put a comment here for writeLine. Prints string pointed to by ds di. Then we just change our calls to writeLine to, instead of putting this in dx, to put it in di. And assuming that di can do that, then we should be all set to go. Here, it built the file. Now, so no longer do we have a $sign at the end of this guy, right? So quit is now terminated with a 0. And then we have here, so C3 is still our right number function that doesn't exist yet. And this is now our, so the rest of this is our function to write a string. So we should be able to actually test this now. So we have those values. So now if I hit most keys, we're not going to see anything. If I hit quit, it clears. If I hit C, it clears. If I hit T, though, we should get those little lines printed out. Next time, we'll create the routine to print a number and get the program to run. Subscribe or come back often to catch the next video. Post any questions you have in the comments below, or come follow me on GitHub. Have fun out there, and keep on crafting.